Thank you very much. So my name is this here, Jeong Han Kim. So I'm very much honored to give first talk or first workshop of Sangil Ohm's IBS. What is the discrete math group? Okay. So today I'm gonna talk about Poset. This is Poset. So formally partially ordered set. So here are formal definitions, but you may consider forget about this. You can just compare and non-compare. Some pair we can tell which one is bigger, which one is smaller. For some pairs we cannot tell which one is bigger, which one. So that's partially ordered set. So and if we have one more property, so that every pair is comparable, then it is called totally ordered set. Okay. So totally ordered set has these four properties. So previously, partially ordered set has or partially ordered set has only three properties. Okay, so totally ordered set is sometimes called total order or linear order or something like that. So here are some examples. This one is this. Okay, so I can use the other one for over there. Okay, I can use both. Okay, so if we have three elements and only one relation, that's also partially ordered set, but because to make this one partially ordered set, we need this trivial relation. And another example is this one, and the third example is this one. Even though I wrote these two relations, because of transitivity, A is less than C. So you can imagine. So even though we have only three elements, the writing is sometimes difficult to understand. So picture tells a lot of things, though we should explain the picture a lot. Okay, so for example, as you can imagine what this is. This is this relation. Okay, partial ordered set. So A is less than C. We cannot compare A and B. We don't know which one is bigger. And here is another one. C is the biggest, bigger than A, bigger than B, but we don't know which one is bigger between these two, maybe. So this is called Hassa diagram. So this E is not U, so it's Hassa. Okay, so this kind of Hassa diagram. So now we are going to consider a linear extension of a Posets. Linear extension is totally ordered set that contains all the relations of partially ordered set. So for example, if we consider one linear extension of this partially ordered set, can be this. So to make linear order, to make this partially ordered set linear ordered set, B can be here, here, here. We have three choices. Yeah, please. Another $1,000. Okay. So this is one example. B is here and here, here. And for this one, linear extension of this one is one linear extension can be this one. The other one can be B here and A here. That's linear extensions. So first question is, given partially ordered set, so how many linear extensions do we have? Before that, we should know there is at least one linear extension. So here is the theorem. Every partially ordered set, partial order or partially ordered set can be extended to a total order. So I proved it by example. Okay. Another example. So I proved twice. Okay. But this can be constructively proved using some topological sorting algorithm. And for finite set, for infinite partially ordered set, we need Asimov choice to prove this. So we know there is one for every poset. So question is, how many linear extensions do we have? For example, this poset. So as I told you, it has three. The B can be in three positions, here, here, here. So that we have three linear extensions of this one. Same thing. So for this one, it's obvious. A can be less than B and B can be less than A. So we have two choices. So we just use notation L of P is the set of all linear extensions of P. So for example, for this one, this linear order and upside down here. So B is here, A is here. That's L of this partially ordered set. Oh, I can use this one. No? Oh, right. Okay, and we write E of P is equal to the number of linear extensions. So number of elements in linear extensions of partial set. We are going to use this notation. This means PR means probability. So there is broken one, so I can use broken one. So suppose we have partially ordered set and linear extension of P. Then in some linear extension, X is less than Y. And in the other part, Y is less than X. Then this PR X less than Y means ratio of this one. So you can just imagine. This is just, it's not fancy way, but it's just a way to write counting. It's nothing but counting. After that, after we count number of linear extension in which X less than Y, divide by the number of linear extensions. So it's just, it's probability, but it's quite easy probability. It's just counting. It's not easy, easy to define, not easy to understand. For example, what is probability of B less than A? B can be, as I said, B can be here, here, and here. We have three choices. Among these three, B is less than A only once. So probability B less than A is 1/3. By the same argument, probability B less than C should be 2/3. So question. Again, this is definition of this PR X less than Y. Question is, how large of these minimum? So what is the maximum? Normally, if there is one relation, then maximum is 1. No? So minimum is important because it's split linear extension. So we are interested in probability X than Y and probability Y less than X. Minimum of these one. For example, can you find a pair X, Y so that this minimum is half? Can you? Yeah, there was you cannot in general. Sometimes if you are lucky you can, but not always. Because here the number of linear extension is only 3. Then we cannot get 1/2 at all. So all numbers are 0, 1/3, 2/3, and 1. I almost said that 3/3, but okay. So half and half is not always possible, but then half and 1/3, how about 2/3? Okay, half and half is not always possible. By this trivial example, easy example, it's not trivial, so easy example. So next question is, even if it's not half, then it should be third. So there is 1/3, 2/3 conjecture. So for any partially ordered set, can you find a pair so that this minimum is always bigger than or equal to 1/3? Okay. That's 1/3, 2/3 conjecture, meaning you can solve it. You can try, because nobody else proved it. So this is conjecture to many people. Then this is still open, not solved, but Brightwell, Felsner, Trotter proved this one. So instead of 1/3, 2/3, we have this strange number, which is, I don't remember. So can somebody compute what this number is? Okay. Anyway, so it's not exactly 1/3, 2/3, but we can do something, even though it's not exactly 1/3, 2/3. Again, the conjecture is open, but we can prove this one. So now I came to real problem. Real problem is this. So given we have poset, so some pairs are comparable, but some pairs are not comparable. Then we can consider linear extension. I mean, not we. You can consider linear extension. Just one linear extension. Then I can guess what the linear extension is. Of course, just random guess may not work. It's very small possibility. But I have tool. Tool is this one. Is x less than y in your linear extension? Again, it's not good idea to choose x, y, which is already, the relation of them are already known in the poset. So it's good idea to choose incomparable pair of poset. So I will keep asking this question. Is less than xy? Of course, the choice of xy will be different every time. So I don't ask the same case question twice. Though you can ask me the same question twice. Then I will answer 3 times. Okay? So anyway, so using this kind of question or query, I try to find your linear extension. Unknown linear extension, I don't know. So what is the best strategy? What is best strategy for me, or what is your best strategy for you? So if I choose x and y, then your answer can be the bigger part, always bigger part, because you wanna leave more possibility, so you can hide more. that's your best strategy. Then my best strategy is opposite of this one. I just choose xy that split this linear extension almost evenly if possible. But that's not always possible because of previous theorem, 1 such 2. But we can still choose a pair xy so that this is true. Then let's say this is delta. Because the theorem says we know there is this pair for any partially ordered set, so I choose that one. So this one is 1 minus delta, this one is delta. Then whatever the answer is, I always eliminate delta portion of remaining possibility. Then how many times do we need? So this is why we have log. Yeah? So log. So if I do that, where is my slide? I talk too much. Yeah, here we have this one. Delta is this number. You have seen this. Then if I choose pair like this, then I eliminate at least delta portion of linear extensions. Then how many times do we need? These many times. This is the original initial number of linear extensions. So each time we just eliminate at least delta. But on the other hand, as I said, you cannot eliminate more than half. In worst case, of course, if you like me and you are friendly, then you can give me nicer answer. But I don't think so. Yes, yeah. So, in the worst case, we cannot eliminate more than half. So, this is lower bound, and this is upper bound. So this strategy cannot be improved more than 2/3 here because we have example there. Okay, so number of for the best queries, for best sequence of queries, the number of queries required is at least this many, and most this many. So the difference is, what is the difference between these two numbers? Just constant. Okay. So difference constant. But the argument here is at least one weak point. We know there is a pair xy such that this is true. But this is so we know there is Sansam in a mountain. That doesn't mean you can find Sansam, ginseng. Okay, that doesn't. Otherwise, you are going to be very rich. Even though you know there is gold in the mountain, but you need to find it. So then one naive way to find this kind of pair is we can try every pair and compute this probability. Okay, that's one way, a nice way. But even though this way, using this way, you can find gold in the mountain, but hopefully before you die. I'm not sure you can find it before you die, because it's it requires very long time to compute this probability. How long? Have you heard about MP complete or sharp P complete? So many people believe it's extremely wrong. So it will take almost forever. That's not only belief, it's belief. Okay, it's belief. It's because nobody proved. But many people, at least most people, including myself, believe that it takes too long. So we need another way to, instead of using this kind of argument, because it takes too long to find a nice pair, we need another way to eliminate, to find unknown linear extension. So to do that, we introduce entropy of posets. So entropy poset is quite difficult, quite hard to define, because we have to consider chain polytope of CP. Okay. So here is definition of chain polytope, which is a little bit complicated. The chain polytope of poset is subset of unit cube and defined by this relation. And for every chain, every chain means linear order inside our partially ordered set. So it should satisfy this relation. Okay, it's a little bit difficult to understand if you haven't seen this one. If you have seen this one, it's not very difficult. So you may not be familiar with this kind of notation. So here is an example. So I just use examples only. So this is a chain, and this is another chain. This is not chain because we don't know which one is bigger. So we have two chains. So chain polytope is simplex, not simplex. It's simplex, and the polytope satisfying this one. Again, picture tells a lot. This one. Here is the axis of G of A and G of B and G of C. Then we consider this relation, this polytope. And so if you see this inequality and this picture, then you can imagine some kind of geometry. Okay, so you can just draw this kind of things. Relatively easy one is this. For if our poset itself is a chain, which means poset is totally ordered set, then we have this relation. For every chain means we can take this C P itself because P is totally ordered set. Then COP is standard simplex. Standard simplex is this. Xi and this. It's this in 2 dimension. This is standard simplex. 3 dimension, you can guess. I cannot draw. And something like that. You can at least imagine this one. 좀 덥네. Anyway, so I'm not gonna. Anyway, so we can define chain polytope for every poset. Then we define entropy. So chain polytope itself is a little bit complicated. Definition of entropy uses chain polytope, and definition is not extremely complicated, but it's not simple either. So it's a normalizing factor 1 over n and minus log xi and minimum of all of them. So this is a little bit complicated, but by telling entropy, you can get something at least. Anyway, so if P is totally ordered set, and then I have told you chain polytope is standard simplex, and if we have no relation, then it's unit and Q. So entropy of totally ordered set is this minimum of this over all all x in the simplex. So we may take each xi is equal to 1 over n. Then the entropy of totally ordered set is log n. And entropy of non-relation poset is 0 by taking xi is equal to 1. Okay? Because it's unit Q. Okay. So first thing is this. This is very nice thing. So we have used this is result by my advisor Jeong Han and myself, and we found this one. So have you seen this one before? We have seen before a long time ago. Where is it? Here. Though I haven't written the base here, it doesn't matter because there is constant here. So number of linear extension, log of that is, we can bound the number of linear extension using entropy, lower bound and upper bound, only constant factor difference. So we hope instead of using this one, which is hard to compute, we wanna use this one. So why do we need, why this is very good? Because entropy is computable in polynomial time. So as I said, E of P is not computable in polynomial time. I'm not sure, but it's not, at least it's not known. So nobody knows how to compute number of linear extensions in polynomial time. But everybody, except myself, everybody knows how to compute this one in polynomial time. So instead of using this one, we plan to use this one. That's the plan.
So when you compute the entropy, it is within certain error or given error?
Yeah, given error in polynomial time and something like that. So the error, the 1 over epsilon. So if we compute within epsilon, then it requires 1 over epsilon times something like that. So almost exactly. And another property, so we have shown this one. Another property of entropy is this. So this is not right notation, but it's very good to understand. So you can imagine what this means. We have partially ordered set. We added one more relation, and then we consider transitive complete. We need transitivity, so we add more relations there. So I think it's mathematically it's not very good, but for understanding in the slide, it's very good definition. And so this means when I choose the pair x and y, whatever the answer is, so either this one or this one is answer, definitely. Then we can increase whatever the answer is. We can increase entropy by C of n. So we can choose a pair that increases entropy by C of n, regardless of your answer. and this C is almost 0.2. Then we keep increasing entropy by choosing this nice pair. Okay. So because we can increase entropy by C over n, almost 0.2 over n, then we can keep increasing the entropy, and eventually will be the entropy of the totally ordered set. Then we found the totally ordered set we want. Okay. That's the plan, and so that's what it is. And so for every poset P has pair xy such that which increases entropy by C over n, regardless of UNs. It's almost the same argument as before. So we know we have nice pair. So next question is how to find them. But entropy is easy to compute. We can compute these one for every pair xy. So I just compute this one for every pair. It requires only n squared times basic number of computation, which is still polynomial time. So we can find it. We can try. So before I ask any question, I compute this one for every pair, and then choose a pair that maximize this minimum. Then by this theorem, I can increase the entropy at least by at least C of n, and keep doing that. And this theorem and not thank you yet, and this inequality together, I can find dual linear extensions, hidden linear extension. That is the and actually in polynomial time. Okay, so that's end of my talk. Thank you.